Dante Certification Program Level 3. In past levels of Dante certification, you were introduced to the concept of layered network models. We looked at the OSI model and the DoD model before. In this module, we will delve deeper into understanding these layered network models. This diagram we see here should be fairly familiar to everyone who has ever set up an analog audio system. We have XLRs here that take the signals to and from devices, plugged into various I/O boxes, plugged into a master stage box, and then ultimately plugged into a patch bay, and eventually onto multiple snakes. We could look at our data network the same way. Here we have UDP ports that connect to various data applications. These then connect to IP addresses, which in turn connect to our MAC addresses. In fact, a data network is very similar to the way we would wire up an analog network. We also have different devices on different layers of the network, just like in an analog system. We have firewalls that manage the ports at layer 4, we have routers that manage our IP address connections at layer 3, we have switches that manage our MAC addresses at layer 2, and then we have the physical layer. That's our copper, our fiber, and our RF links. That is layer 1. The first step is to understand why layered models underpin networks. On the right, you can see the OSI model, which has 7 layers. We can see that these layers don't map exactly the way we perceive our networks to be. There's more detail here than what we really need. By contrast, DoD or TCP/IP model is very compact and fits exactly into how we're working with our audio networking system. So the TCP/IP model is actually a better fit for what we're doing with audio over IP. Network communication is considered as passing data down the sending stack and passing it up the receiving stack. Here we have a microphone connected on the application layer. The microphone is supplying data to the application layer. Then we send this data down the stack, across the network, and then up the stack where we have a loudspeaker attached to our application layer. Layered models are very much related to IP encapsulation. Encapsulation and layered models go hand in hand, and they are of utmost importance when it comes to understanding modern networks. Let's look at the same examples from before. You can see we put the data through the application layer. This data is then put into a UDP datagram, which is then put within an IP packet. That is then put within an Ethernet frame. We then send it across the network to the receiving end, where at the network access layer, we extract the frame from the network. Then the packet is extracted from the frame, following which the datagram is extracted from the packet. Then finally, the data is extracted from the datagram at the application layer, where our loudspeaker is. So there are 2 models to consider. First, the OSI model, which has 7 layers, and then the TCP/IP model, which has 4 layers. So why have 2 models? The answer is because neither models fully represent what's exactly going on. The strength of the OSI model is that it covers any kind of communication system, not just an IP communication system. But the simpler 4-layered TCP/IP model is very specific to IP, which is why it matches well within our audio over IP systems. So why bother learning both of these models? Why not just learn the TCP/IP model, which appears more relevant to audio over IP? Well, for a software engineer, it makes sense to focus on TCP/IP model. However, for a network engineer, the OSI model can be very useful regardless. The OSI model was proposed in the early 1970s. It is hardware independent and a conceptual model. The nice thing with conceptual models is that they last a long time as opposed to concrete models. The OSI model is great at defining the lower layers of the network stack. such as how we physically signal, how we deal with port addressing, and how we deal with network addresses. But it's not that great for upper layers. In the past, we used to have a separate application layer to the presentation layer, but that doesn't really exist anymore. The TCP/IP model is newer. It's great at defining these parts, but it lacks details down here at the network access layer. So the key thing is, it's best to have an understanding of both models. If you're looking to focus on being a network engineer, then having a good understanding of OSI model is better. If you're leaning towards the software application side, then understanding the TCP/IP model is better. Now, having spoken of these network models, let's bring the conversation back to what audio engineers understand best. We are quite familiar with the idea of an input list. We see it on the right here. If we look at this as an abstract of the layered models, we can see that we have channel numbers. This could be considered as being the application layer at the front of house desk. Now at the stage end, the application layer is the instrument. Then we have some information that says how to encapsulate the signals. Now this is just like the layered network models we looked at. In this example, we have stuff from the top of the network stack feeding into the network stack. And we see it pop out at the other end. As long as it works fine, we don't really care. Now of course, in an analog rock and roll situation, we will have a line check before the sound check. This too is similar to a network, specifically commissioning a network and then taking the network to the next stage. Unsurprisingly, a lot of functionality around how network functions is similar to how things were done in the analog world. So on the network, we have the consideration of different transport layers. We could be using TCP/IP or UDP/IP. Now this doesn't matter so much in terms of what we're doing with the audio. We would normally use UDP because we make that determination based on the transport size. In an analog system, we would care about the voltage of the signals. So I would probably use a separate multicore to a separate return score. The reason being that my microphone level signals are going to be very low voltage and could suffer from crosstalk. I would certainly separate the return score from the main cable for one of two reasons. First reason is that it could be taking a totally different path to the amplifier, and secondly, there could be very different voltage levels. This way, I would have more control over my grounding path as well. So we can think of a UDP stack as a multicore. In fact, we have 65,536 ports in each direction to play with at each IP address in both UDP and TCP transports. Here we could feed our multiplex signal onto one UDP port as illustrated here. We could then have multiple stage boxes, each with their own stack. Here we have two lots of 65,536 in both directions. So effectively we have four 65,536 multicores, which we have inside the stage boxes. We could have an Ethernet stack on the other end where we have 65,536 ports in each direction inside the mixing console, also connected to the switch. We can then use a routing software to connect whichever the ports we need to.